This is a schematic diagram of what students typically would do to analyze an unknown liquid. So students are given each one an unknown liquid and labeled with a number. So the first thing to do is to either do an IR or boiling point determination, and if the IR is available, you can collect the IR spectrum, and then after that collect the NMR if it's available. So after IR, you can determine if the unknown is an alcohol because of the intense absorption band at around 3600, and then if you have a carbonyl for a ketone, or an ester because there's an absorption band at around 1700. And then the same thing for an aldehyde, you have a absorption band at around 1700, but additionally you can see a weak to medium aldehyde absorption band corresponding to the CH at about 2700. So the NMR can also confirm the presence of an alcohol or an aldehyde. So after IR, you can now proceed to do the chemical tests or the classification tests. If you have an alcohol, you're going to go through this on the left side, and then you can do Jones oxidation because that will confirm the presence of either primary or secondary alcohol. And then additionally do a iodoform test because that would determine if you have what is called a methyl alcohol. So then if you have a C double bond O, it's going to be either ketone, ester, or an aldehyde. But then you can already eliminate, if you have an aldehyde, you can eliminate ester or a ketone. So then the presence of a C double bond O for either a ketone or an aldehyde can be done by using a 2,4-DNP test. That would be positive. And then a iodoform test is specific for a methyl ketone. And then if you have an aldehyde, there are several tests available. And as you can see, this is the most reactive functional group for this unknown. So first you can do 2,4-DNP test to confirm C double bond O. And then you can do also Jones oxidation because that will be oxidized by the Jones reagent. The aldehyde becomes a carboxylic acid. Then 3 tests specific for aldehydes would be Tollens, Schiff's, and Fehling's test. That would be positive. For the ester, there's only one test, which is the alkaline iron 3 hydroxamate test. Assignment of unknowns for experiment 3 as a virtual lab experiment. The unknowns are labeled as A to F, and it's going to be either an aldehyde, a ketone, an alcohol, or an ester. Everyone will work on 2 unknowns, and everyone will work on unknown F. However, if your last name starts with A to E, you're going to be working on unknowns A and F, last names F to J, B and F, last names K to O, C and F, last names P to T, D and F, and the last one, last names U to Z, unknowns E and F. Boiling point determination of a liquid. The procedure is shown in the handout in here. So I'm going to set it up using an unknown liquid, and then we are going to add it in a reaction tube, calibrated reaction tube, and then I'm going to attach a thermometer, and then as shown in this handout, we're gonna boil it using a sand bath. So I'm going to use the reaction tube in the micro kit. So each student will have a kit, and I will be using one of this reaction tube. It's actually calibrated, has a label. And then I'm gonna put the liquid, which is labeled as unknown E. So this is the liquid unknown E. And then to demonstrate the boiling point determination. And I'm going to add 1 boiling chip And then this is now the setup. So we are going to boil the liquid in a thermowell with a sand bath. The sand bath is attached to a transformer, and we're going to set it to 120 volts, and then that's attached to the power outlet in here. And then I'm going to set it to about 50. So 50 at the back, set up to 50 in here. For now, because we don't know really the boiling point of the liquid. So if it doesn't, if we did not reach yet the boiling point, we are going to increase the setting for the transformer. From the micro kit, I already took out the reaction tube, so I added 8 drops of the liquid, and then I also added 1 piece of boiling chip. From the micro kit, I'm going to be using this piece in here, which is a connecting adapter. And then there's also a rubber adapter in here. And then I'm going to just snap it. And then I will also use this other adapter. And I'm going to be using a thermometer that goes up to 260. So this thermometer in here goes up to 260. So then I'm going to insert it into this adapter slowly. So this is now the liquid in the reaction tube, and then I also have the boiling chip, and then I inserted the thermometer, and the bulb of the thermometer is sitting at about the 1.0 mil mark of the reaction tube, and then I don't have it entirely closed, so I have like an outlet for the vapor, and then I attach the thermometer using the adapter, and it's not touching the sides. I don't want it to touch the side, and I want it to boil. When it boils, I'm measuring the temperature of the vapor or the liquid. I'm measuring the temperature of the liquid when it boils, and it's touching the bulb in here. So I'm going to put it now in the sand bath and clamp it. So the setup is I don't want the thermometer to be measuring the sand or the sand bath. So I have it higher than the sand bath, than the level of the sand bath. And the temperature is really just, it's about 23, 25. That's the room temperature. So we can still see it. So this is 100, and then 200 and 260. Control the heatings. I'm gonna shield it with aluminum foil so it can heat up fast, and so to avoid like any draft coming from the outside air. But I also still want to see the boiling of the liquid. It's like a shield. So I had the setup pretty much shielded with aluminum foil so I can heat it up fast. So it took about 10 minutes, and now it's steady at about, the temperature right now is about 98. So it's steady for about 2 minutes. And then we're gonna let it go for another 3 minutes. If it doesn't go up, that's gonna be the boiling point of the sample. So after another 3 minutes, so it's like 5 minutes or so, the temperature did not go up. It's now 98. So the boiling point of the sample is about 98 degrees C. And as you can see, the sample, it's actually refluxing. So you can see the reflux up. It's refluxing on the side, so it's evaporating and then going down into the solution down, and so basically that's the boiling point of the sample. So it's washing the bulb, And the thermometer bulb is measuring the temperature in which the sample or the liquid is evaporating and condensing. So it's kind of like refluxing it. So it's the boiling point of the liquid. So again, the boiling point is the point at which the boiling point was steady at about 5 to 6 minutes. If it doesn't go up, then that's the boiling point of the sample. This is Jones oxidation for alcohols and aldehydes. This is a test to determine the presence of alcohols and aldehydes in the unknown. So we have 3 standards that we are going to run simultaneously with the unknown. So ethanol, CH3CH2OH is a primary alcohol. 2-propanol or isopropanol is a secondary alcohol. This is the structure. And then anisaldehyde is an aldehyde. This is the structure below. So those are in here. Ethanol, 2-propanol, and anisaldehyde, para-anisaldehyde. And then we have the Jones reagent over here. So I already put 4 drops of each of the unknowns. So we have A, B, C, D, E, F. So I have here in this tube ethanol, 2-propanol, and then anisaldehyde. So I put already 4 drops of the unknown and then 10 drops of acetone. So this would be unknown A with 4 drops of the unknown. So typically in a face-to-face setting, you are going to have unknowns and it will be in a vial. It's going to be labeled as a letter or as a number. In this case, we have a letter. So A, B, C, D, E, F. And then I put already 4 drops of each of the unknown and then 10 drops of the acetone. And then you will run this simultaneously with the standard, 3 standards, ethanol, 2-propanol, and anisaldehyde. So I already add 4 drops of the unknown and then 10 drops of the acetone. So this is the Jones reagent. This is actually CrO3 or chromium oxide. So this is chromium oxide, chromium plus 6 is the oxidizing agent. The reagent is orange in color. Okay, and then I will add, so we will take note of the time that it takes to react. So ethanol should react and 2-propanol as well as anisaldehyde. So 2 drops. So you heard that pop. It's quite reactive. And then I'm going to put the cork. And then, okay, cork. And then finally the aldehyde. So, gonna shake it a little bit. Shake. Shake. So, ethanol on the left and then 2-propanol on the right. So they turned green or blue-green in color. So it reacted. It actually got oxidized by the oxidizing agent. However, the anisaldehyde, it did not pop. Okay, so it did not change color. But we let it sit. So basically, these 2 reacted fast. However, it's turning color, as you can see, but it's slow. So the aldehydes will react, but slower than the alcohols. So primary alcohol, and then secondary alcohol, ethanol, and 2-propanol. So those are the standard. So now we are going to check now what are the functional groups in each of these unknowns A, B, C, D, E, F. Okay, so 2 drops of the reagent. Okay, you see it bubbling. Okay, so it reacted fast. So it changed. You can see the coloration like dark green on top. So this is unknown A. You can see that greenish color on the side. So now let's do unknown B. So unknown B, again, 2 drops of the reagent. So 2 drops of the reagent. So you see it actually reacting. So now there's a greenish kind of color on the side. Okay, and then unknown C, the same thing. We're gonna add 2 drops. So it's intensely orange in color and no reaction. So we let it sit, but if you compare A, B, C, so you can see that C is orange. A and B reacted, C did not react. Okay, and then we're gonna do D this time. So again, 2 drops. Okay, it's quiet, no popping sound. So same, C and D did not change. And then we're now doing E. So E, 2 drops again. So nothing. And then last one is F. So 2 drops. So that's A, B, C, D, E. So A and B reacted, C, D, E, no. F reacted. It's not as intensely green as A and B, but it reacted. So again, these are standard ethanol, 2-propanol, and then anisaldehyde. Tolerance test for aldehydes. This is a reagent containing 5% silver nitrate. We're looking for a silver mirror, which means the production of a silver 0. And it looks like a mirror, and it's silver. And we're going to add sodium hydroxide and ammonium hydroxide. Is in basic solution. And the standard that we are using is the aldehyde at the bottom, shown here. So again, anisaldehyde, this is the functional group. So the reagent for tolerance test is 5% silver nitrate. And then I already added a ml of the silver nitrate in each of the tubes. And then I'm now going to add 3 drops of the sodium hydroxide. So 3 drops sodium hydroxide. So it's going to be basic. So it formed a precipitate. I'm going to add ammonium hydroxide until that precipitate dissolves. So I'm going to count the number of drops. So after I added ammonium hydroxide, 20 drops, it dissolves. So now I'm going to add the standard anisaldehyde, 3 drops. So I'm tilting it slightly because I have drops on the side. And I don't want to agitate it. And I'm just really mixing it gently because I want to see the deformation of the silver mirror. This is now the standard anisaldehyde with Tollens reagent. So you can see that the side of the tube actually has a silver kind of precipitate, which is indicative of the silver zero and the change in the appearance. And on the tube you can see also the shiny silver zero. So this is the standard. So now for the unknowns, I added the silver nitrate. So I added sodium hydroxide, 3 drops. And I also added a ml of the ammonium hydroxide. And when I shake it, the precipitate, brown precipitate disappears. So that is now the solution. It's clear. So I added the base sodium hydroxide and ammonium hydroxide. This is the solution before I shake it. So this, the precipitate at the bottom is brown. And then if I shake it in here, if I vortex it, it will dissolve. So that is now clear. So I'm now going to add in each of the tubes 3 drops each of the unknown. So I added all the unknowns in each of the tubes, A, B, C, D, E, F. So this is A. So nothing. Clear. And then this is B. Nothing. And then this is C. Nothing. And then D. Nothing. And then E. Same, nothing. And then F. So this is the unknown F. This is the Schiff's test for aldehydes. So it's testing for the presence of a functional group, which is the aldehyde. So it will be done on the unknown and also the standard aldehyde, which is shown at the bottom, the structure, and it's anisaldehyde. So we have the aldehyde functional group attached to the benzene. We're going to set up several test tubes for each of the unknown, and then we're going to add 20 drops of the Schiff's reagent, and then add 1 drop of the test compound or the unknown, and then observe any color change. So I have here the Schiff's reagent. So we have the unknown samples labeled as A, B, C, D, E, F, and then the standard, which is the anisaldehyde. So right now, I only have the Schiff's reagent, 1 ml. I added in each of the tube, and now I'm going to add the unknown, 1 drop of the unknown in each of the tubes. So unknown A. So I'm just going to add 1 drop. And then shake it. And then unknown B. One drop. And then unknown C. One drop again. and then shake. So let's do the standard. So I will add 1 drop of the standard anisaldehyde. Then shake. Then let it sit. So now let's go back and do unknown D. 1 drop. Shake again. Then unknown E. A drop. Shake. Then the last one, F. Shake. So now let's observe the results. So this is the positive test for aldehyde, which is a magenta color for the standard anisaldehyde. So you see the color of the anisaldehyde, it's magenta in the white background. And now we compare. So now if you compare, F is intensely magenta color, while A, B, C, D, E did not change color. So you see A, no change in color. B, no change in color. It's the same color as the reagent. So that's just reagent. So if I pipette it up, it's very light yellow, almost colorless, very pale yellow color. So nothing changed, did not form a complex with the reagent. Again, A, B, C, D, E, no change in color. F, magenta in color. And then the anisaldehyde, which is the standard, is also magenta, also changed in color. This is now the iodoform test, and this is the test for the presence of methyl ketones. The standard that we're using is acetone, shown at the bottom in here. So it has a methyl and a ketone. So it should test positive, meaning that we should see a yellow precipitation, and that's indicative of the formation of iodoforms. Iodoform is yellow precipitate. Iodoform is CHI3. I already added in this large test tube 4 drops of each of the unknowns, A, B, C, D, E, F. And then I also have a standard, which is the acetone. So acetone is the standard. And then I added 4 drops of it. And then I also dissolved this in 1 ml of methanol. So methanol, I put 20 drops or 1 ml using the calibrated pipette. So this is 1 ml. I also added 1 ml of sodium hydroxide. So 10% of sodium hydroxide, because it has to be in basic solution. I am now going to add the iodine in potassium iodide. So this is the iodoform reagent. I will do first the standard, which is the acetone. So I added about 10 drops. So you can see the yellow precipitation of iodoform already. So that's the positive test. And now, so I added 10 drops. So I'm going to do now for each of the unknown. And then I'm going to shake it. So it's different. Okay, so I don't see yellow precipitation. So I'm going to do for all of the unknowns. So B, I'm now doing B, unknown B. So 10 drops. And then C, unknown C. Just going to add first everything and then we will compare the results. And now I'm going to go back to A. So A, I don't see anything. So sometimes it's slow to react, so we might have to add another 10 drops and see how it works. Actually, if I can tilt it, you can see that there's precipitate at the bottom. And then D does not have any precipitation. It's clear, almost clear. And this one slightly yellowish but no precipitate. E, and then F also nothing. So I'm gonna add on each 10 more drops just to increase the amount of the iodine. So 10 drops. I will not add any more on this because I already see a precipitate on C. But I will add on D. Okay, so this is D. And then E. Last one, F. So let's go back in here. So nothing on A. And then on B, I see some. So on B, you can see that there is now formation of the precipitate. It was a little bit slower than C, but I can see now actually, if I tilt it, you can see it at the bottom. Again, C, you see quite a bit on here. And then D, nothing. It's very clear. And then again, E, nothing. And then F, there is some turbidity, but I don't see any precipitation. So let's go back and compare with acetone again. So this is now the acetone, which is the standard, and you can see the yellow precipitate. And again, this is the acetone. Okay, acetone. And from our results, actually, it's the B sample, B unknown. Also has precipitate at the bottom. You can see after it's settled. So this is B, B, and that's the precipitate at the bottom. And then also C, this is unknown C. Okay, you can also see precipitation at the bottom. A test for aldehydes and ketones is the 2,4-dinitrophenylhydrazone test, or the 2,4-DNP. So we're going to perform the test on the unknowns, and then on a standard aldehyde and ketone, we're going to add 3 drops of the test compound in a tube and then add the reagent we're looking for the formation of an orange-yellow precipitation, which indicates the presence of an aldehyde or ketone. The standards used for this test are shown below. The structures are shown in here. The aldehyde is anisaldehyde. This is the aldehyde functional group. And then 2-butanone is the ketone. So we have the unknowns labeled as A, B, C, D, E, F. And then we have an aldehyde standard anisaldehyde. And then 2-butanone ketone standard. So I have here the anisaldehyde and then 2-butanone. So I already put 3 drops in each of the tube, and now I'm going to add the reagent, which is 2,4-DNP reagent, 2,4-dinitrophenylhydrazine reagent. So I'm going to add 10 drops each. So first, let's do it on the anisaldehyde, and then I'm going to add 10 drops. Shake a little bit so there's an orange precipitation. It's an orange precipitate for the aldehyde. And then 2-butanone. So again, 10 drops. So you can see precipitation at the bottom. It's yellow this time. And then we're going to do now A, B, C, D, E, F for the unknowns. So I'm just going to add it and then we'll observe. And then the last one, F. So let's review the result. So this is now the anisaldehyde standard. And it's dark orange precipitate. It's actually the color of pumpkin or carrots. And then the 2-butanone also form precipitate at the bottom, although it's yellowish in color. So now for the unknowns A, B, C, D, E, and F. So A is completely clear, no precipitation, so A. And then B, again the same, no precipitation at the bottom, nothing, it's clear, yellow. The reagent is colored yellow, but if there's a reaction, there's a precipitate. So C, unknown C, has a precipitate which is orange, like color of pumpkin, C. And then D, also the same, unknown D, also the color is orange, precipitate. Unknown E, clear, nothing. And then unknown F is turbid, so there is some indication of precipitation, but the precipitate is small. So again, F also formed, and it's yellow precipitate at the bottom. So it's turbid. Valence test for aldehydes. We are now going to run this test on all the unknowns and then the standard aldehyde. And standard aldehyde shown in here at the bottom is anisaldehyde. This is the functional group aldehyde. And then we are now going to combine or mix together the Valence solution A, which is copper 2 sulfate, and then with Valence B solution, it's potassium hydroxide, it's basic. And then we are going to add 2 to 3 drops of the test compound on each of the tube. So we're going to add 2 to 3 drops of the unknown and also the standard in each tube. And then we're going to heat it and then we're gonna heat the tubes to boiling for about 10 or 15 minutes. We are looking for the formation first of a pale green color, followed by the formation of reddish precipitate of cuprous oxide. So the copper was reduced from copper plus 2 to copper plus 1, and that copper plus 1 is red in color, which indicates the presence of an aldehyde. So I now have a standard anisaldehyde in here, which is an aldehyde, and the reagent is Fehling's A solution. Fehling's solution A, it's copper 2 sulfate, it's blue. And then we have the Fehling's B solution, it's actually basic because of the potassium hydroxide. So I have in here the tubes already, and I already mixed together here Fehling's solution A and Fehling's solution B for the unknown tubes A, B, C, D. So this one is just Fehling's solution A, and then if I add the Fehling's solution B, 10 drops, it becomes very intense blue color as shown on the left for the tubes A, B, C, D. So in here, this is the color, like the color of my gloves, and then if I add the potassium hydroxide, 10 drops, it becomes very intense blue color. So if I shake it, it becomes very, like, almost purple color. Very nice blue color. So this is the standard anisaldehyde. So I'm going to add 3 drops in here. So I just mix it up, I just vortexed it, and then, so I'm gonna do the same thing, A, B, C, D, F. So these are our simple, so I'm gonna add 3 drops. So that's unknown B. So that's unknown E. And finally unknown F. So this is now unknown F. So let's mix it up, and then we're going to boil it for about 10-15 minutes. So we are now going to boil the solutions into the water. So about 10-15 minutes, I'm just going to dip it in here. We're looking for a greenish color first and then a red precipitation. So after boiling it for about 10 minutes, I took out A, B, C, D, E, and nothing really changed to it. It's still dark blue. So A, B, C, D, and E did not really change color. So this is the unknown F. And you can see the precipitate if I tilt the tube. So you can see the precipitate actually at the bottom, which is reddish in color. So against the black background, you can see the top has a red precipitate of the copper plus 1. So that's F. And then the same thing for the anisaldehyde, you can see that red coloration at the bottom. So this is the anisaldehyde standard, and that's the color copper oxide, copper 1 oxide at the bottom. So again, F, has the red precipitate at the bottom. This is now the alkaline iron 3 hydroxamate test. We are going to run the test with a standard ester because this is the test for the presence of a functional group, which is the ester. So the ester is ethyl benzoate, which is in here. So this is ethyl benzoate. It's clear, liquid. And then we are going to put 4 drops of each of the standard or unknown in each of the tubes, and then we're adding 10 drops of the hydroxylamine hydrochloride solution in alcohol, and then 2 drops of 6 molar sodium hydroxide. We're going to heat it to boiling to about 5 minutes, then add 20 drops of 1 molar hydrochloric acid. If cloudiness develops, we are going to add 1 ml ethanol, then add 1 drop of iron 3 chloride or FeCl3 solution. Mix it, and then if there is a red, blue, or purple color, it's a positive test for esters. So the structure of ethyl benzoate is shown in here. There's a benzene and then C double bond O ethyl. So I have the standard, which is ethyl benzoate. So hydroxylamine hydrochloride, I'm going to add 10 drops. And then I'm going to add 2 drops of sodium hydroxide, a base. So I shake it, and I already added in here 4 drops of each of the unknowns labeled as A, B, C, D, E, F. I already added 10 drops of the hydroxylamine hydrochloride solution in alcohol, and then also 2 drops of 6 molar sodium hydroxide. So I already have a water bath heating in here. Temperature is close to 70. So I'm now going to immerse the tubes and then heat it for about 5 minutes. So after heating it up for 5 minutes, I will now add 20 drops of 1 molar hydrochloric acid on the standard and then also in the unknown. So 20 drops of 1 molar hydrochloric acid. Okay, and then shake it. There's a little bit of cloudiness, but I think it's not too bad. So I think I'm just gonna add the 10% iron 3 chloride. Okay, so I'm going to add 1 drop. So iron 3 chloride is yellowish in color. So now I have a purple color. So that's the positive test for the presence of ester. So that's what we're looking for a positive test. So now I'm going to do now the unknowns. So 1 drop of the iron 3 chloride. Okay. So no purple coloration. It's just orange. So we're looking for a purple color. So deep purple. So nothing, it's just red, reddish. So C, unknown C. So yellowish. And then D. So yellowish, nothing. And then now E. So E turned purple, reddish purple color. So that's E. And then F. So F stayed yellowish. So no formation of a complex with iron chloride in the presence of hydroxylamine. So that's our test for the presence of an ester. So A, B, C, D, E, F. So this is the standard ethyl benzoate, and then only E changed color to a red, blue, or deep red, blue, or purple color. Ethyl benzoate is our standard ethyl benzoate. Final analysis of the unknowns. The chemical test data will provide information as to the identity of the functional group. The unknown can only contain one functional group. It's going to be either an alcohol, a ketone, an aldehyde, or an ester. Then confirm that functional group using the IR data. Next, using the boiling point data and the table of boiling points provided, you are going to draw possible structures of the unknowns. Then, use the NMR data to identify the R groups in the assigned unknowns, and the R groups in the alcohol, ketone, aldehyde, or ester can be aliphatic or aromatic and can range from 2 carbons to 7 carbons. Aliphatic means straight chain or cyclic, or the aromatic structure is going to be a benzene. And then write the final lab report following rubrics.